This video is part of a series of videos presenting solutions of problems related to the machine dynamics topic. This video presents the solution of a problem, dealing with the design of a flywheel starting from a moment crank angle diagram. The problem here deals with a torque crank angle diagram for a one-cylinder 4-cycle engine. It is given that the nominal speed of the engine is 250 radians per second, and that the area of the shaded rectangle is 6,300 Newton-meter degrees. It is asked: first, to calculate the average torque. Second, to calculate the maximum torque. Third, to find a suitable value for the flywheel mass moment of inertia using a coefficient of speed fluctuation of 0.1. Fourth, to find the speed at theta equal 180 degrees considering that the speed in the beginning of the cycle is equal to 237.5 radians per second. Let's collect first the given data. First we have that the nominal speed is 250 radians per second. And we have the shaded area is equal to 6,300 Newton-meter degrees. Also, we have the coefficient of speed fluctuation is equal to 0.1. The first question asks to calculate the average torque. Here, the height of the shaded rectangle is equal to the average torque minus 40. The shaded area is equal to T average minus 40 times 180 degrees, which is equal to 6,300 Newton-meter degrees. Solving the equation for the average torque gives T average is equal to 40 plus 6,300 divided by 180. Hence, the average torque is equal to 75 Newton-meters. In the second question, it is asked to calculate the maximum torque. We recall first that the average torque is 75 Newton-meters. The average torque corresponds to the constant torque that delivers the same work as the varying torque. Thus, the average torque is equal to T max times 180, minus 50 times 180, plus 40 times 180, minus 50 times 180. Divided by 720, which is equal to 75 Newton-meters. Simplifying by 180 gives T maximum, minus 50, plus 40, minus 50, divided by 4, is equal to 75 Newton-meters. Solving the equation for T max gives maximum torque is equal to 75 times 4, plus 60. Thus, T max is equal to 360 Newton-meters. In this third question we are asked to consider a speed fluctuation coefficient of 0.1, and find a suitable value of the flywheel's mass moment of inertia. Let's first recall that the maximum torque, that was calculated in the second question, is equal to 360 Newton-meters. The mass moment of inertia of the flywheel is given by W divided by CS omega n square. CS is the speed fluctuation coefficient and is equal to 0.1. Omega n is the nominal speed of the flywheel, here it is equal to 250 radians per second. W corresponds to the critical energy that should be stored, or that should be delivered, by the flywheel, in a part of the cycle. Here the critical part of the cycle is between 0 and 180 degrees. Thus, W corresponds to the blue shaded area. Please be advised here, that diagram is not given to a scale. To calculate the area in joule, we need to consider angles in radians. Thus, W is equal to 360 minus 75 times pi minus 0. Working this out with a calculator gives W equal to 895.35 joules. The mass moment of inertia is then equal to 895.35 divided by 0.1 times 250 square. Using a calculator gives I, the mass moment of inertia, equal to 0.14326 kilograms meter square. Let's move now to the fourth and last question. It is asked to find the speed when theta equals to 180 degrees. Knowing that, in the beginning of the cycle, the speed is equal to 237.5 radians per second. Thus, in the beginning of the cycle, at theta equals 0 degrees, the speed is equal to 237.5 radians per second. And we would like to determine the speed at theta equal to 180 degrees. A change of angular velocity is equivalent to a change of kinetic energy of the flywheel. Neglecting any dissipative force, any change of kinetic energy is equal to the external work. This last equation writes the conservation of energy. The change of kinetic energy delta K is equal to the kinetic energy at theta equal to 180 degrees minus the kinetic energy in the beginning of the cycle, or K 180 minus K0. Thus, the change of kinetic energy is equal to I times omega 180 square divided by 2 minus I times omega 0 square divided by 2, where I is the mass moment of inertia of the flywheel, which was calculated in the question 3. I over 2 is a common factor of the two terms. Hence, the change of kinetic energy is equal to I over 2 times omega 180 square minus omega 0 square. The mass moment of inertia of the flywheel was calculated in question 3, and is equal to 0.14326 kilograms meter square. The work between 0 and 180 degrees corresponds to the shaded blue area, and also was calculated in question 3. It is equal to 895.35 joule. Substituting numerical values, making omega 180 as the subject of the equation, and working out, using a calculator, gives omega 180 is equal to 262.5 radians per second. This value is 5% higher than the nominal speed. It is quite expected as the speed fluctuation coefficient is equal to 0.1 or 10%.